Hi, ladies and gentlemen. Welcome to lesson 34. This lesson is going to be a little bit different than what we've done in the past. What I'm doing is making a recording that will play during class time. I've done this in the past, not for Math 344, but in previous courses, and we're just going to give this a little bit of a go here and see how we like it. So let me start with the conversation somewhat leading off of what we did on Friday. So I want to talk a little bit about this piece of code. This is very similar to what you're going to need to do for the final project. So I recommend for this entire video that you're taking notes as we go. And then after we're finished, if there are any questions, we can certainly address those. So this piece of code starts with the mread command. You'll need to use that command, and what that will do is read in an image, which will be a color photo. And then the RGB to gray command is a command that changes the color photo into a grayscale photo, which is basically a black and white photo. And I'll explain, the double and the division by 255 and all of that. We'll have that conversation later during the final project, but that's going to be a required item. You're going to be able to use the singular value decomposition function, the SVD, and then you're going to need to come up with some information with respect to how we're going to actually do this. But what I want to do right now is just demonstrate to you one of the items that was in one of Professor Brunton's lectures. And so he was talking to us about knowing how many singular values we want to keep during our truncation. This is a graph similar to what we have seen in the past, where we have singular values on one side, and it appears we have a little over 1,700 singular values for this particular photograph, and we can see the energy component here. And what he does, what you can see right down here under number of singular values, I have used the Gavish-Donohoe criteria in order to select the number of singular values. And again, Professor Brunton in his video references the paper by Gavish and Donohoe, which gives us some indication as to how many of the singular values we want to keep. And so this is the command for me that is doing that. Let me show you. This is the paper. If you want to write this down, it's actually a pretty short address. This is the IEEE paper that he is referencing in his video, which is the Gavish-Donohoe paper on how many singular values we should select. If you don't want to copy this down, it's fine. I'll just dump it into the team, and then you can grab it from there. So I've used that, and now let's take a look at what the image is going to be. This is a more complicated image with respect to the number of pixels than what we were looking at on Friday. And the methodology for this is similar to what we were doing. We have the original image is over here on the right-hand side, and then this is our singular value piece here. I'm going to turn off the video for a second while we run through this, because I know you don't have to see it come into focus again. All right, this is almost done. So we used 560 of these 1,757 singular values, which is this Gavish-Donohoe criteria for truncation. And the idea is that we should have what is basically an exact duplication of our image except for the noise. So let's take a look at this. We're going to zoom in again, and I'm going to come down here and select the bat. So that's 2, 3, 4, 5, 6, 7, 8, 9, there's 10, and I'll select the bat over here in the same area. 2, 3, 4, 5, 6, 7, 8, 9, 10. So I'm looking at this part, for example, of the bat, or this piece up here, and you can see that these are almost on a pixel by pixel basis exactly the same. There are some slight variations, but not really very much. When you look, for example, in here at the pixel layout, it looks nearly identical to what's over here. And that's true for all of the pixels. So this is a nearly identical replication given the truncation that we used. And I calculated the error associated with this it doesn't pop up. But the relative error on this image is in the range of 0.2% if you compute pixel by pixel. All right, so I want to show you that because somebody asked about something that we were working on last time and wondered if we could do a color image. So what I want to do is just show you the difference on doing a black and white image versus a color image. I made a speculation on Friday as to how that would work, and it turns out that the speculation is actually accurate. What you'll notice is we have over here, we're going to read in the file. I'm immediately going to change it over to a double, and that brings me to one item here. So there's the whos command in MATLAB. So the whos command gives us what are the active variables. So this is from what we did before with the black and white photo. This gives us what are the variables, what are the dimensions, and what type of variables do we have. So for example, we have the data input, right? This is what we read in, the actual picture file I have in is data. And it's this thing right here. So it's the 1757 pixels by 2454 pixels by 3. The reason there are 3 in here is because there is one matrix for each color, each of the primary colors that we used for doing computer graphics, which are red, green, and blue. It's called RGB color. And the type of units that we have are actually uint8. They're not double precision numbers. They're integer numbers that we actually have to convert over to being doubles. That's why the double command is in here. If I put double around a number, it'll automatically convert it to double precision. That's in MATLAB. And so we can see that the black and white image is indeed what we had. So let's go back to the previous one here. So here we just read in the data. We didn't put the double around it, but we put the double around the black and white. So it converted the uint8 into a double. And then we changed it, of course, to a black and white image. And what that does is instead of having the 3 different colors, we now just have one grayscaled image, which is the data BW for black and white. And then, of course, the matrices in here for doing the singular value decomposition. Here's an enormous matrix. So if you look at the size of this, this is a 20 gigabyte matrix. And if we look at the memory usage, right now we're up to 25 gigabytes on my computer. So this may not actually work on your computer. The reason I did this is I was able to make a different matrix for each of the basis functions from the u and v. So it's the u times v transpose that I have here, and that's what's created all of these images. It makes for the animation that I was showing you to run faster. That's why I did it. So let's go back here, and in the colorized version, what I'm going to do is immediately convert the input data into double precision. So I'm going to take it off of uint8 and make it double precision. And then what I need to do is, I have, remember, 3 data frames, one for red, one for green, and one for blue. I need to do a singular value decomposition on each one of those color frames. And so I have my red and my green and my blue. And then I pull out the singular values, and the process of rebuilding everything looks very much the same, but I have to do it 3 times. So for example, when we build the approximation here, we have to do an approximation, but we have to do 3 of them, one for each color. So there's the approximation for the first data frame, basically, which is red, and then the second one is green, and the third one is blue, and then we can feed all of that information back into the imshow command. So this is another command you're going to use, is the imshow command. And in the case of the color photo, I actually have to change the picture back to uint8, change the data back to uint8 in order for it to show up correctly. In the black and white, we do not need to do that. We actually have to leave it as double when we're using a black and white picture. So these are some of the differences, but what I want to show you is how this works out when we are running and having the same image. All right, here I have the singular value decomposition, and I have actually done the different singular values for different colors using red, green, and blue. You can see a little bit of color variation. Not surprisingly, the singular values are quite close to each other. There is a little bit larger singular values here in the red domain, at least initially. So that's part of what we're looking at. Again, I'm using the Gavish-Donahoe criteria right here in order to figure out how many frames I'm going to keep. And I'm scoring off of the green color because, as it turns out, the green color makes up the largest percentage of the black and white image. So I decided to use the green as my coloration. And what you'll notice is this is the color image here. So this is the actual image and this is the frame. So let me start this and we'll take a look at this evolving similar to what we did with the black and white. It's got the number of singular values in, and then we will need to pause the video because this takes quite a bit of time. There's not enough room in my computer for me to pre-build those basis matrices like I did for the black and white image. So it looks like we're up to almost 200, so let me pause this. All right, we're almost at the end. There we go. We've reached our 560 singular values. So this is an image actually of when my family lived in Australia, and my friend here, Don Brown, Coach Don, Coach Brad, myself, we were the baseball coaches for the Little League team. And the surprising part of this image, which is why I selected it to be the example of a color image, is this is in the middle of the outback in Australia. So once you get off of the watered fields here, you can see in the background the mountains, which have some, well, they're really hills, but they have some red stone in them because all around is iron heavy soil. All right, so that's what I wanted to show you is that this idea of the image compression is not something that's just related to black and white images. This was, again, a question that somebody asked on Friday. Let's just quickly take a look at the who's here. You will see the relative error. I did calculate the relative error for the color image, and it's right here at about 0.2%. So these are the matrices that I used and what their dimensions are. And so we have the singular value decompositions, of course, the U and V matrices for each color, and those are used to stitch together and make the approximations. And then, of course, the original image coming in, which I convert immediately to double, and that is a 1757 2454 by 3. So it's the same exact file that we were loading previously. So what I want to do now is shift to taking a look at some of the information here from Professor Strang's text and just to make a couple of notes. So in general, the section 7.2 is talking about the singular value decomposition, how exactly we do it, and we will talk about the 4 fundamental subspaces. It's not a big surprise that when we have AV equals U times sigma, which of course is the same as A is equal to U sigma V inverse, and in this case it's V transpose. As I told you in videos previously, you'll see this as a unitary matrix called the Hermitian, which is defined as the transpose but conjugate, just in case you have complex matrices. In this case, we never have complex matrices. We're only talking about matrices with real entries in them. And what we can see then is the information that leads to the results that are inside of what Professor Strang's talking about here with respect to the fundamental subspaces. So it's pretty easy to see that the column space, if you think about this, this is just linear combinations of the columns of A created by the columns of V being multiplied in. So we have V being multiplied in and giving us linear combinations of the columns of A, and those linear combinations are just the columns of U. So as long as we have non-zero singular values lined up with our U columns, then those columns must be part of the column space of A. And in fact, they define the column space of A. And we'll talk a little bit more about this when we talk about our example. And then, of course, any vector here, v, that maps to a 0 singular value must be part of the null space of A. Because if I multiply by a vector times A and I get 0 out of it, then by definition I have a vector that's in the null space. So the null space of A is kind of over here in the V's, and the column space of A is over here in the U's, and we'll look more specifically at those items. Not surprisingly, Professor Strang provides the same breakout with respect to the approximations that we were talking about. So he gives all of the rank 1 matrices that are associated with this process, and it all lines up with what we've seen before. He includes the proof of the SVD, so that is somewhat illuminating. It goes hand in glove with one of Professor Brunton's conversations, the one where he talks about the correlation. And really the conversation there is pretty straightforward, but it's important enough for me to identify the key components for you. So consider that we would have this singular value decomposition. If I were to take A transpose times A, to take the transpose of this product of 3 matrices, what I'm going to do is I'm going to swap them all around and then take the individual transposes. So what I would get is U sigma V transpose transpose, and then of course just a U sigma V transpose. Well, you know from earlier in the course, to do this I'm going to reverse the order here and then take the transpose of each of these matrices. But the transpose of V transpose is of course just V. The transpose, I mean, I can call this transpose, but the transpose of a diagonal matrix is of course the same matrix. So this is just sigma again. And then finally I have U transpose. And then I'm going to multiply that by U sigma and V transpose. So this is illuminating just to see it one time and to walk through it for yourself. But what you'll notice here is U transpose times U is equal to the identity matrix, because U is an orthogonal matrix. So where this leaves us is V times sigma squared times V transpose. And that's equal to A transpose A, which now fully explains why we follow the procedure that we do when we calculate singular value decomposition. One more step here, A transpose A, I'm going to right multiply by V. Multiplied times V is equal to V sigma squared. And what does this look like to us? Right, this is just like an eigenvalue eigenvector decomposition. A transpose A is diagonalizable. And we notice that V contains the eigenvectors. So the eigenvectors are in there, and the sigma squared values are the eigenvalues. This is why we approach the problem by solving with A transpose A and looking at the eigensystem. So similarly, if we consider AA transpose, that's going to be U sigma V transpose V sigma transpose U transpose. So I'm just reversing the order. Again, this is the identity matrix, and where we end up is AA transpose equals U sigma squared U transpose, right-hand multiplication by the U matrix, and we end up with U is equal to U sigma squared. And again, we have an eigenvalue problem where the eigenvectors for AA transpose are contained in U, and the eigenvalues are equal to sigma squared. So this is really the underpinning of why the singular value decomposition works. We're not going to prove anything, but it's extremely enlightening to see why the eigenvalues for both A transpose A and AA transpose are the same, and then the relationship with the eigenvectors and the left singular values down here in U and the right singular values in V. So this is the whole machinery behind how things work. And so he's outlined that on page 372, and then some more here on 373. And then he also walks through an example. I'm going to leave that for you to take a look at. The next piece here on 374, he talks about what he refers to as an extreme example, an example with a zero singular value and a zero eigenvalue, and then relates how the singular values and the singular value decomposition and the eigenvalue decomposition are different but related. Then he also talks about, and this is very important, which is the stability of singular values versus eigenvalues. So the eigenvalues are inherently an unstable way to think about matrix decomposition. It's not to say that eigenvalues and eigenvectors aren't valuable. They're very valuable. We'll take a look at that on Thursday. But what we have here is as we discussed previously, we have this ridiculous get out of jail free aspect to what we're doing, because no matter how bad our A matrix is, what we're considering for the singular value decomposition are the eigensystems associated with these really stable matrices, right? These matrices are symmetric, they're positive semi-definite, they're really nice matrices to be dealing with. So that is kind of what saves us with respect to this conversation about instabilities. And then he goes through a little bit more about the kind of comparing the singular values of A and the eigenvalues of these symmetric matrices that I've circled in blue here. So on the next page here, page 376, Professor Strang talks about some information that I gave you previously, which has to do with the finding of eigenvalues and singular values by using the fact that we have symmetric positive definite matrices. So the eigenvalues satisfy this maximum ratio that we discussed before with the energy, and as we did in class, if we restrict ourselves to x vectors that have a length of 1, then we can go hunting around and using this methodology to find eigenvalues. And from that, of course, we're searching for eigenvectors, and we can find the eigenvalues. And then we can subtract off the rank 1 matrices that are associated with this, and this allows us to kind of continue the process. So this is an interesting conversation. He also talks about how we find singular values in a similar manner, where we maximize the ratio of the vector norm, ax, again, divided by the norm of x. So if we select vectors that are length 1, then we can just look at maximizing a times x. And this is something that has a nice geometric interpretation. Imagine for a minute that we were looking for singular values for some 2 by 2 matrix, whatever it might be. Okay, so this is some matrix A. Well, where are the vectors in 2 dimensions? So I'll say that this is x1 direction and the x2 direction. So where are the vectors that are unit vectors? Yeah, right. The unit vectors all lie on the unit circle. The vectors of length 1 are all the vectors that start at the origin and come out to the unit circle. And so what we're trying to do to find the first singular value is find the maximum, and we've already selected all the x vectors with norm 1. We're trying to maximize this a times x norm. We're trying to find the maximum norm. Well, this is actually pretty easy to do. We could just chop up the unit circle and go around 100 times or 1,000 different cuts here. So we could pick an angle, for example. This is how it is done. We could pick an angle that is maybe 2 pi over 100. And what we're going to do is multiply this times I, where I is going to go from 0 to 100. And then we would cover 0 to 2 pi, and we would go all the way around. And then what's our vector? Well, you know how to make this vector from all the years of calculus and algebra that you've had, right? I can just go in the x direction here, the x1 direction, a cosine of theta I and a sine of theta I. And that would give me all of these vectors, and I could just sample them and find out which one gives me the largest value. Again, this is not how it's done, but this is the correct geometric picture of what it is we're talking about. Which of these x vectors, when I multiply it times a, gives me the maximum. So that's just an idea of how we can think about this information that Professor Strang has provided for us. And then finally, over here is a concept associated with how to think about this kind of in a block methodology. It's worth the read, but it's not something that you're going to be tested on. It's not part of what we're covering. And then finally is this portion down here, which I told you to ignore, which is how things are actually computed. The computation of eigenvalues and eigenvectors is actually quite difficult, and it's not something that we cover in this class. It's a numerical linear algebra topic. As always, when we finish up here, Professor Strang does a nice job of providing us a review of the key ideas associated with this section. And so we can just read them out, right? We understand what the decomposition looks like for singular values. We understand that we're going to order the singular values from largest to smallest. They're always all positive or zero, and the larger ones are the more important ones. And then also, how do we find the singular values, and how do we find the left and right singular vectors? And that's all associated with this information here, and we're going to do a practice problem momentarily. And then, of course, the rank 1 decomposition and the conversation about the norms and maximizing these norms in order to find the singular values. Kind of the direction, if you will, of most importance of the linear transformation. That's really what we're doing. We're taking any linear transformation and we're breaking it down into a series of linear transformations. It's really a sum of linear transformations, kind of most important to least important. And that's the whole idea of the data compression that we've been talking about. All right, so now let me throw up an example. All right, here we go. We are going to calculate the singular value decomposition for this matrix. Go ahead and pull out a sheet of paper, or just add into the notes that you've already been taking for today's class, and write down this matrix, and then we're going to begin. Remember, where do we start for this process? We need A transpose A and AA transpose. Those are the two things we need to calculate. So now that you have the A matrix written down, I'm going to swap screens and crank this out. Let's go. So here's what I have for the two matrices, and we can verify and make sure that we have those correct. Remember, we know they're going to be symmetric, so if we come up with something that's not symmetric, then we have something that's incorrect. Also, as we noticed, the A transpose A and AA transpose matrices have the same eigenvalues, except AA transpose, as we see here, is a linear combination of these two linearly independent vectors. So even though we have 3 columns, those 3 columns are all built from these 2 vectors. So AA transpose has rank 2. So we already know one of the eigenvalues here is equal to 0. So the 2 non-zero eigenvalues will be equal to the eigenvalues here. So our next step is to pick on the smaller matrix, which in this case is the 2 by 2, and find the eigenvalues. Let's go. Remember, you want to be practicing these by hand. If you don't think that I can test you on hand calculations for eigenvalues and eigenvectors, trust me, I can. So let's take a look at what we have. In this case, then it's the determinant of a minus lambda I. Set that equal to 0. We come up with the characteristic polynomial. So this is our characteristic polynomial right here. And in this case, we have one that factors easily. And the result is we have a 9, a 4, and of course we have the 0 associated with the larger one. And now what we need to do is find the eigenvectors. So starting with lambda equals 9, and remember, from this, let's put it in blue here, we end up with the actual information that we want for the singular value decomposition. In this case, the singular values are 3 and 2 and 0. They are the square roots of the eigenvalues for these matrices that we have over here. We write down what I have. I have an 8, 2, 2, 5. So our matrix is 8, 2, 2, 5, and we need to find the eigenvector. Eigenvector for 9 and the eigenvector when the eigenvalue is 4. Go ahead. All right, let's take a look at what we have for these two eigenvectors. So applying the eigenvalues, we come up with these two eigenvectors here. And now that we have those eigenvectors, we can certainly build the V matrix. Right, so the V matrix is a 1 over the square root of 5, and oftentimes I'll put the 1 over square root of 5, the 1 over length, to make them unit vectors over on the right-hand side, just because it's easier than trying to jam that in front of it. But now that I know where I'm going with this, we have the 2, 1, and the negative 1, 2. And so this is my matrix V right here. And I could have, of course, told what V2 was going to be because I know it has to be orthogonal to V1. That's one of the requirements for the eigenvectors of symmetric matrices. Now what we're going to do is lean upon what is arguably one of the more important calculation pieces for singular value decomposition. So we know that AV is equal to U sigma, but when we take this column by column, we have A times a column here. So some column of V is equal to the same column, whatever that might be, in U, multiplied times the appropriate singular value. And this is, instead of calculating U vectors as the eigenvectors of AA transpose, it's actually faster and easier to do it this way. So we have the V's now, and what we're going to do is we're going to take and multiply our A matrix. So let's remind ourselves of what the A matrix is. We're going to multiply this A matrix times the individual V's and set them equal to the singular value times the U's. So for example, let's do this first one together here. For example, we're going to take the A and multiply it times the first V vector, which is a 2 over the square root of 5, 1 over the square root of 5, and that is going to be equal to whatever our U vector is going to be, our U1 vector times the singular value 3. So we'll do this multiplication and solve. So go ahead, complete this one, and then do the next one as well. All right, so now that we have U1 and U2, which we have calculated in this manner, we know we're looking for a U3 vector. Several different ways to find this vector, but in this case, I think the easier way to do it is to figure out what vector is orthogonal to both U1 and U2. So what I'm going to do is just logic my way through this, and then I'll figure out what the division by the magnitude is so that I can get a unit vector out of it. But looking at U2, there's only two ways for me to be orthogonal to U2. Either the first entry is a 1 and the last entry is a 2, and it doesn't matter what the middle entry is, or the first and last entries are both 0. Those are my only choices. And then I would have a non-zero entry for the, well, if I have the first and last entries here, the first and last entries are 0, and I have a non-zero in the middle, there's no way I'm orthogonal to this one. So in order to be orthogonal to U2, I must have a -1 and, a +1, sorry, a +1, and a 2. Because now, regardless of what the length is, when I do this dot product, I'll end up with a 2 minus 2, which gives me a 0. So now all I need to do is figure out what value I need in order to be orthogonal to U1. Well, I have 2 plus 8, that's 10, is equal to 5 times this middle entry, so the middle entry is going to have to be a -2. And so now I can verify, right, that's 2, 0, -2 for a dot product is 0, and that's 2 minus 10 is -8, plus 8 is 0. And then here I can see 4, 8 plus 1 is 9, square root of 9 is 3. So those are the 3 U vectors that we have, and from those we can create a U matrix. So the U matrix is equal to, and this first one's a little bit of a hassle, so it's 2 divided by 3 square root of 5, and 5 divided by 3 times the square root of 5, and 4 divided by 3 times the square root of 5. And then I have a 2 over square root of 5, 0, -1 over the square root of 5. And then finally a 1/3, a -2/3, and 2/3. And so that's our U matrix. So now what we can do, we have all the components. And so this is the important thing to realize, is we have the singular values, we have V, and we have U. And let me just walk through here what we have. So we found the eigenvalues, we found the singular values. Using the singular values, we found these eigenvectors. And then using this powerful relationship between the left and right singular vectors, we're able to calculate what the left singular vectors are equal to. So the first left singular value, and you can see I wrote it a little bit differently. I moved the radical 5 up to the numerator, and then the second one is here, and then the third one we have, which is orthogonal to the first two. So I can build the two matrices, which are what I've just finished doing. And now what we want to do is write down A as V, A times V equal to U times sigma. And so this is AV times U sigma right here. Here's my V matrix. And then I have my U matrix, just as we discussed here, multiplied times the sigma matrix, remembering the sigma matrix contains the singular values in the order that I solved, which is always largest to smallest, and it's the same dimensions as the A matrix. And then, of course, I can take this equation and multiply by V transpose, which is V inverse on both sides, and come up with this formulation here. All right, so that's the methods for calculating singular value decomposition. Obviously, for any large matrix, we're going to use the computer to do this. However, there's a lot of insight to be gained in doing these small kind of 2x2, 2x3 problems, because we see how the construction of A transpose A and AA transpose leads to the singular values, gives us zero singular values when they exist, and how we can easily gather up these eigenvectors which are orthogonal to one another. So the last thing I wanted to look at here is, what does this really look like from the standpoint of the vector spaces? So this is part of what's covered by Strang in and I want to do it with this specific example, what's covered in section 7.2. So let me stick with the blue pen here, and what I'm going to do is, this is going from where, right, R2 to R3, because A is 3 by 2. So it's mapping from 2 to 3. So from R2 to R3. And now what we want to know is what are the bases? So if we come back and look at the singular value decomposition, how can we find the bases for each of these spaces? Well, this is almost easier to see in this version, although we'll look at both. But looking at this, what we see is that the null space of A doesn't exist because I have as many columns as I have non-zero singular values here. So I have 2 columns in V and I have 2 singular values, and so I have no null space. So the null space over here, the null space of A is just the trivial null space. It's only the 0 vector. Similarly, the column space, as we discussed before, is equal to the span of which vectors? The first 2 vectors in U, because I have 2 non-zero singular values. And if you look at the matrix multiplication, it's very clear. If I do this matrix multiplication, I'm going to get 3 times the first column and 2 times the second column. The third column gets multiplied by 0 in both cases. So the third column here is not part of the column space of A. But because U is an orthogonal vector, what is the third column? Well, I know that the 4 fundamental subspaces are orthogonal to one another. This is how MATLAB and most other programs find these bases for the fundamental subspaces, is by using the singular value decomposition. And so this is the null space of A transpose, and that is equal to the span of the remaining vector, or in general, every column of U that's associated with a 0 singular value. And then, of course, the column space, or rather, sorry, the row space, so the column space of A transpose, which is the row space of A, is the span of all of the vectors in V. So this is the span of V1 and V2, all of the vectors in V that are not associated with 0 singular values. So in this case, neither of these columns is associated with a 0 singular value. So from this decomposition, we can find out what the different pieces are in the 4 fundamental subspaces. Let me show you another example.